2.5 million years ago, a star walked into our solar system. Not near it, inside it. It came close enough to reach into the frozen shell of comets surrounding everything you know, and it shook that shell the way you'd shake a snow globe. We are still living inside the wave it started. New research now points to a second star, one whose closest pass to us may already be written into the sky above your head tonight, closer than the last one ever came. By the end of this, you will understand exactly how astronomers found the fingerprints of a star we never saw arrive, what it threw loose, and why the next encounter might not be a memory. It might be a countdown. Get comfortable. Hit subscribe if you're new here, because tonight the solar system stops feeling like a sealed room. Now let's slowly ease into this. Part 1. The star that should not be there. Picture the sky exactly as it is tonight. Quiet, fixed, patient, every star in it holding its position the way it has held that position for as long as anyone alive has been watching. That is the illusion. It is a beautiful illusion, and it is completely wrong. Every star you can see is moving. Some of them fast enough that if you could watch across 100,000 years instead of a human lifetime, the entire sky would rearrange itself in front of you like a slow, silent storm. Most of that motion is harmless. Stars drift past each other across gulfs of space, so enormous that even a close approach means nothing. Trillions of kilometers of nothing between us and them, forever. That is the normal condition of a galaxy. Isolation, distance, silence, but not always. Every so often, rarely enough to feel impossible, and often enough to be certain, a star's path bends close enough to matter, close enough to reach past the outer edge of a neighboring solar system and put its hand, gravitationally speaking, on things that do not belong to it. We are now fairly confident that this happened to us, recently on a cosmic clock. Recently enough that a member of the human family tree was already standing upright on this planet when it occurred. The star responsible carries a catalogue number instead of a name, which is a strange kind of anonymity for something that may have quietly altered the future of your solar system. It is called HD 7977. It sits in the constellation Cassiopeia, a little more than 250 light years from where you are lying right now. If you had a serious telescope and a clear night, you could find it. It would look like nothing. A faint, ordinary point of light, indistinguishable from 1,000 others scattered across the same patch of sky. It is not ordinary. It is close to a twin of our own sun. A G-type star, slightly heavier, slightly poorer in the heavier elements that get cooked up inside earlier generations of stars, but structurally, thermally, almost a sibling. If you swapped it for the sun, nothing about how a star behaves would look strange to you. And 2.5 million years ago, give or take, that star was not 250 light years away. It was inside our solar system, not inside the region where the planets orbit. Farther out than that, in a place so distant and so cold that most people have never been told it exists at all. A vast shell of icy debris that surrounds everything you think of as the solar system, the way a soap bubble's skin surrounds the air inside it. We will spend real time in that region tonight, because everything about this story depends on understanding what it actually is. But hold the shape of it for now. An outer shell, icy, ancient, fragile, and a star walked through part of it. Here is the part that should genuinely unsettle you before we even get to the mechanics. We did not detect this event when it happened. Nobody watched it. No ancient astronomer recorded a strange visitor in the sky because at the distance involved there would have been nothing to see. No flash, no warning, no visible sign at all. A star passing through the far outer reaches of another star's territory does not announce itself. It does its work in silence, in the dark, over spans of time too long for any single observer, human or otherwise, to notice as an event rather than a background hum. We only found out about it because of a spacecraft that had no interest in comets at all. It was built to do something almost absurdly patient, measure the exact position of more than 1 billion stars over and over, year after year, with a precision fine enough to detect motions smaller than the width of a hair seen from a mile away. That spacecraft is called Gaia, and it belongs to the European Space Agency. Its job was cartography. Draw the most precise map of the galaxy's stellar population that has ever existed. It was not hunting for close encounters. It found one anyway, because once you know exactly where a star is and exactly how fast it is moving in every direction, you are no longer limited to knowing where it is now. You can run the clock backward. That is not science fiction. It is arithmetic, applied at a scale that makes it feel like something else. Take the star's current position. Take its current velocity in 3 dimensions. Multiply, invert, and you get a trajectory. Run that trajectory back far enough, and for most stars, nothing interesting happens. They simply recede into a past position exactly as unremarkable as their present one. For HD 7977, something interesting happened. Wind the clock back roughly 2.5 million years, and its calculated path runs directly toward us. Not near us, toward us. Directly through the neighbourhood of the Sun. At a distance close enough that the encounter stops being a footnote and starts being an event with consequences. And here is where the story should have ended, cleanly, with a headline and a tidy number. It did not, because the measurement carried an uncertainty large enough to make the entire question meaningless on its own. Small errors in a star's measured motion do not stay small when you run them backward across 2.5 million years. They compound, they stretch. A star's velocity, measured today with extraordinary precision, still carries an error bar so tiny it seems irrelevant until you multiply that tiny error by 2.5 million years of travel. Then it stops being tiny. It becomes the difference between a glancing brush and a direct hit. The honest range that fell out of the Gaia data was almost embarrassingly wide. The closest approach could have been as near as roughly 2,300 times the distance from the Earth to the Sun. It could also have been as far as roughly 13,000 times that distance. Those are not 2 versions of the same story. They are 2 completely different solar systems. One in which a stellar intruder tore violently through the heart of our comet reservoir. One in which it barely grazed the outer edge and left almost nothing behind. Astronomers were left holding a confirmed encounter and no way to say how serious it had been. That is an uncomfortable place to stand, and it is exactly where this story picked up. Because if you cannot pin the star down directly, precisely enough to know what it did, there is another way to ask the question. You stop looking at the star. You start looking at what it might have left behind. You look for the wreckage. And the wreckage, if it exists, is not hidden in some inaccessible corner of the galaxy. It is arriving in our sky right now, tonight, in the form of objects that most people glance at maybe once in a lifetime and never think about again. Comets, specifically, the rarest and strangest category of comet there is, the ones making their very first approach to the Sun in the entire history of the solar system. untouched, unheated, fresh from wherever they came from. That is where two independent teams of researchers went looking for an answer the star itself could not give them. And what they found in that catalogue of first-time visitors is the reason this story does not end in the deep past. It is the reason it reaches directly into the risk calculus of the world you are living in right now, and into a second star already measured, already tracked, and already on a course that some analyses say will bring it closer than the first one ever came. We will get to that star. First, we need to understand the place these comets actually come from, because almost nobody, even people who consider themselves reasonably well informed about space, has an accurate picture of just how strange, how vast, and how quietly fragile that region really is. Part 2. The shell around everything. You have heard of the solar system's planets. You may have heard of the asteroid belt, that scattered ring of rock between Mars and Jupiter. You may even have heard of the Kuiper belt, the icy debris field beyond Neptune, where Pluto lives among thousands of similar frozen worlds. All of that, all of it. The Sun, the planets, the asteroid belt. The Kuiper belt, the entire architecture of the solar system, as it is usually taught to you, fits inside a bubble that is almost embarrassingly small compared to what actually belongs to the Sun. Because surrounding all of it, far beyond anything a spacecraft has ever visited, far beyond anything a telescope has ever directly photographed, there is a shell. An enormous spherical shell of icy bodies, extending outward in every direction, so far that light itself takes more than a year to cross parts of it. It is called the Oort Cloud, named for the Dutch astronomer who first proposed its existence in the middle of the 20th century, not because he had seen it, but because he had done the math and realized nothing else could explain where certain comets were coming from. Nobody has ever seen the Oort Cloud directly, not once. Not with any telescope humanity has ever built, not with any spacecraft humanity has ever launched. It is not that we lack the will to look. It is that the objects out there are small, dark, unlit, except by a sun so distant it provides less illumination than a street lamp seen from across a continent. They do not reflect enough light for our instruments to catch. Scattered across a volume of space so enormous that even trillions of objects amount to a whisper of matter per cubic light year. Everything we know about the Oort Cloud, we know second-hand. We know it the way you might know a room you have never entered, by watching what drifts out from under the door. The things that drift out are comets. Specifically, the long-period comets. Objects on orbits so enormously elongated that a single lap around the Sun can take thousands of years, or hundreds of thousands, or in some cases, millions. When one of these objects finally swings close enough to be seen, it is carrying information. Information about where it came from, and information about whatever it was that knocked it loose from wherever it had been sitting, quietly, for billions of years. Try to hold the actual scale of this region in your mind, because it resists intuition in almost every way. Astronomers generally split it into two parts. The inner Oort cloud begins somewhere around 2,000 times the Earth-Sun distance and extends out to roughly 20,000 times that distance. It is not spherical. It is somewhat flattened, more like a thick, hazy disk than a ball, a kind of transition zone between the more orderly Kuiper belt and what lies beyond. Then there is the outer Oort cloud, which is genuinely spherical, a shell surrounding the entire inner solar system from every direction at once, running from roughly 20,000 times the Earth-Sun distance out to something like 100,000 times that distance. 100,000 astronomical units. Say that slowly, and let it actually register. That distance is close to 1.5 light years. A single light year is already a number the human mind struggles to hold, roughly 9.5 trillion kilometers. Multiply that by 1.5, and you have the outer edge of what still, gravitationally, technically belongs to our sun. The population estimates for what lives inside that shell are staggering in a way that stops sounding like a real number and starts sounding like a rhetorical device. Something on the order of 5 trillion objects, at least a kilometre across in the inner region alone. Roughly 1 trillion more in the outer shell. These are theoretical estimates, built from models rather than direct counts. Because again, nobody has ever seen the cloud itself. But even as rough estimates, they describe a reservoir of ice and rock so vast that the 2 trillion galaxies you might have heard mentioned in some other documentary about the scale of the universe suddenly feel almost proportionate by comparison. Your own solar system is hoarding trillions of small frozen worlds in its own backyard, and you will never see a single one of them directly in your lifetime. Here is why that distance matters so much to this story. At 100,000 astronomical units, the sun's gravitational grip is close to its absolute limit. Objects out there are barely held. They are close enough to be considered part of the solar system, and far enough that almost anything else moving through the neighborhood gets a meaningful say in what happens to them next. The sun is not commanding those objects. It is barely suggesting. Under ordinary, quiet conditions, the thing doing most of the actual pushing and pulling out there is not the sun at all. It is the galaxy itself. This is one of those facts that sounds almost too strange to be real the first time you hear it, but it is well-established physics. At the outer edge of the Oort Cloud, the sun's gravity has grown so weak that the combined gravitational pull of the entire Milky Way, every star, every cloud of gas, every dark matter halo contributing its own tiny share, becomes a force that actually matters. Astronomers call this influence the galactic tide. The galactic tide works slowly. It does not yank objects inward in dramatic bursts. It works the way erosion works, patiently, continuously, reshaping orbits over spans of millions of years until, gradually, a small fraction of Oort Cloud objects find their orbits bent just enough to send them falling inward toward the sun. This is the background process, the steady, quiet trickle of comets that has been feeding the inner solar system with the occasional long-period visitor for billions of years, entirely independent of any passing star. It is the baseline, the normal rate, the rhythm the solar system settled into a very long time ago and under ordinary conditions never really departs from. But there is something crucial buried inside how the galactic tide actually behaves, something that turns out to be the key that unlocked this entire mystery. The galactic tide is not even-handed. It does not tug on every orbit in the Oort Cloud equally, regardless of orientation. Because of the specific geometry of how the galaxy's disk is oriented relative to the sun, and how the tidal force actually acts on distant orbits, the tide pulls much harder on objects whose orbits are tilted in certain directions and barely touches objects tilted in others. It has, in other words, a preference, a directional bias, baked into the physics itself. That means every comet the galactic tide sends inward carries a kind of signature. Not a literal marking, nothing you could see under a microscope, but a statistical fingerprint written into the orientation of its orbit. If you gathered up a large enough sample of long-period comets that had been delivered purely by the slow, patient work of the galactic tide, and you plotted the orientations of all their orbits, you would not see a random scatter. You would see a lopsided pattern, a specific, predictable bias stamped onto the population as a whole, even though no individual comet would obviously reveal it on its own. This is the detail that turned an unsolvable problem about a distant star into a solvable one. Because if the galactic tide has a signature, then anything that delivers comets by some other mechanism entirely, anything that is not the slow patient tide, should produce a population without that signature. A population that looks different. A population that, in a very real sense, is carrying a different fingerprint altogether. And that is exactly the tool two researchers picked up when they gave up trying to pin down the star directly and turned instead to the comets themselves, sorting through more than 200 long-period orbits, splitting them into groups, and looking for exactly this kind of statistical fault line. What they found did not look like the slow, patient work of the galaxy. It looked like something had reached in all at once and shaken the entire shell. Part 3. Reading the fingerprints. There is a particular kind of detective work in astronomy that has nothing to do with pointing a telescope at a single object and hoping for a clear picture. It is statistical detective work. You gather a population, you sort it, you look for patterns that should not exist if your simplest explanation were true. And then you ask what kind of event could produce the pattern you are actually seeing. This is exactly the approach two researchers took when they set out to test whether HD 7977 had really passed close enough to matter. The researchers were Nathan Kaib of the Planetary Science Institute and Sean Raymond of the Laboratoire d'Astrophysique de Bordeaux in France. Their paper carried a plain, almost understated title, A Potential Signature of HD 7977's Passage Among Observed Long-Period Comet Orbits. It went up as a preprint in the summer, and within weeks it had worked its way through the astronomy press, not because it made a loud claim, but because the method behind it was so clever that it was hard to dismiss. Their starting point was simple. If the supply of long-period comets reaching the inner solar system is normally governed by the slow, steady work of the galactic tide, and if the galactic tide leaves a specific, predictable bias in the orientation of the orbits it produces, then any comet population that lacks that bias is telling you something. It is telling you that whatever delivered those comets was not the tide at all. So they gathered the orbits of more than 200 long-period comets, every one observed carefully enough since 1990 to have a reliable orbit calculated. And then they split that catalogue into two distinct groups, based on a distinction that turns out to matter enormously. The first group is what astronomers call dynamically old comets. These are objects that have already made at least one pass through the inner solar system before. They have already felt the heat of the sun directly on their surface, already been baked and outgassed and altered by that first close encounter. And, critically, they have already had a gravitational encounter with one of the giant planets, usually Jupiter or Saturn, whose enormous mass is capable of reaching out and subtly reshaping the orbit of anything that wanders too close. Those encounters pull energy out of a comet's orbit, tightening it, shortening its period, nudging its trajectory into something a little more settled than it was before. The second group is the dynamically new comets. These are the rarest visitors of all, first-time arrivals, objects that have never once been close enough to the sun to be heated, that have never been touched by the gravity of Jupiter or Saturn, whose orbital periods stretch out past 1,000,000 years. They are, in the most literal sense available to an astronomer, fresh. Untouched samples straight from the source, carrying whatever information was written into them at the moment they were dislodged from the Oort Cloud, with nothing since then to blur or overwrite that signal. This distinction turns out to be everything, because it means The two groups are effectively two separate photographs of the same underlying process, taken at different points in time. The old comets, having had more chances to be perturbed and altered, represent an average over a longer stretch of history. The new comets represent something closer to a snapshot of whatever is happening right now, or at least whatever has happened recently enough that the evidence has not yet been erased. When Kaib and Raymond looked at the old comets, the dynamically settled, well-worn population, they found exactly what you would expect from a solar system governed purely by the slow, patient galactic tide. The orbital orientations carried the lopsided bias the tide is known to produce. A signature, present and measurable, sitting right where the physics predicted it should sit. When they looked at the new comets, the fresh arrivals, the first timers, that signature was gone, not weakened. Gone, their orbits came back close to isotropic, meaning spread more or less evenly across every possible orientation, arriving from every direction with no meaningful preference at all. It was as if these particular comets had been shaken loose by something that did not care which way an orbit was tilted. Something that grabbed the shell from every angle at once. Sit with how strange that result actually is, because on its own, this should not happen. If a single steady mechanism, the galactic tide, has been quietly and continuously feeding comets into the inner solar system for the entire multi-billion-year history of the solar system, then the newest arrivals and the oldest arrivals should, statistically, look the same, both delivered by the same hand over different timescales, but ultimately governed by the same directional bias. Instead, the two populations disagreed with each other in a way that a single steady process simply cannot explain. There is exactly one known mechanism capable of producing that disagreement. When a star of roughly solar mass passes close enough to the outer solar system, its gravity, for a brief window of time, becomes stronger in that region than the combined pull of the entire rest of the galaxy. For a geologically short span, that passing star is the dominant gravitational force acting on the Oort Cloud, and unlike the galaxy, a single star has no directional preference at all. It does not care about orbital tilt. It reaches into the shell and pulls objects loose from every orientation simultaneously, producing exactly the kind of scrambled isotropic population the new comets were showing. Underneath this, there is a specific piece of orbital mechanics that explains why a stellar flyby produces a sudden wave rather than a gradual increase. Astronomers describe it using something called the loss cone. Think of it as a narrow gate. It is the specific narrow set of orbits whose closest approach to the Sun has been dragged low enough that the object is actually able to fall into the planetary region and become visible to us. Under ordinary conditions, that gate stays mostly empty. The galactic tide drains it about as fast as it fills, which caps the delivery rate of new comets at a fairly steady baseline, no matter how enormous the total reservoir of the Oort Cloud actually is. A passing star does not respect that cap at all. It refills the loss cone abruptly, violently, and across every orbital orientation at the same moment, which is precisely the difference between water dripping steadily from a tap and a dam breaking all at once. Kaib and Raymond tested this idea the only rigorous way it can be tested, through simulation. They built a model Oort Cloud containing 1 million individual test particles and ran that model forward through millions of years of simulated time, once with a stellar flyby included, and once without. Then they compared the resulting comet populations, each version, against the actual observed catalogue of real comets in our sky. The observed sky matched the version of the simulation that included the star. Not perfectly, and we will come back to exactly where the mismatch lives, but closely enough that the researchers pushed the method one step further, into the part of the study that gives it its real teeth. The amount of scrambling visible in the new comet population is not simply a yes or no signal. It is not just present or absent. It scales. A closer, more violent stellar encounter produces more thorough scrambling. A distant, gentler brush produces less. That relationship meant the researchers could, in principle, run the logic backward. By measuring precisely how thoroughly the new comets had been randomized, how far their orbital orientations had drifted from the tide's expected bias, they could estimate how close the star that caused it must have actually come. Their answer, converted from the model back into a physical distance, placed HD 7977's closest approach somewhere between roughly 6,000 and 10,000 astronomical units from the Sun. Convert that into light years, and you get something like a tenth to about a sixth of a light year. Compare that against where the Gaia measurement alone had left the question. Anywhere between 2,300 and 13,000 astronomical units. An enormous, almost useless range, and you can see immediately what the comets accomplished. They narrowed the uncertainty dramatically, far more tightly than the star's own measured motion, run backward through 2.5 million years of compounding error, ever could on its own. And 6,000 to 10,000 astronomical units is not a distant, glancing brush against the very outer skin of the Oort Cloud. It is well inside it. That star did not pass near the solar system in any loose sense of the word. It passed through the region where our comets actually live, deep enough to matter, deep enough to leave a mark that two independent lines of evidence, one from stellar motion, one from cometary orbits, now both point toward. That is where the confirmation ends and the consequence begins. Because once you know roughly how close the star came, you can start asking the far more uncomfortable question sitting underneath all of this. What, exactly, did it knock loose? How much of it is still falling toward us right now? And how much of that falling debris has already found its way into Earth's path? Part 4. The wave that has not finished arriving. Once Kaib and Raymond had an actual number for how close HD 7977 came, they could stop treating the encounter as a historical curiosity and start treating it as an engineering problem. If a star of roughly solar mass reaches into the Oort Cloud at a distance of 6,000 to 10,000 astronomical units, how many comets does that actually dislodge? And once dislodged, how long does it take for them to arrive? The first question is answered by running the same simulation forward and simply counting. When the researchers modelled the delivery rate a flyby at that distance would produce, the result was not a modest bump. The peak comet flux generated by the encounter came out to roughly 10 times the number of comets the galactic tide alone would send inward during an equivalent stretch of time. 10 times the normal supply dumped into the inner solar system in a single sustained pulse. 10 times sounds abstract until you translate it into what it actually means for the sky above you. It means that for a period of time following the encounter, the rate at which fresh, first-time comets have been entering the observable inner solar system has been running well above what the solar system's normal, quiet background process would ever produce on its own. Not because anything is wrong with the solar system today, because something reached in from outside 2.5 million years ago and changed the delivery schedule. And here is the detail that turns this from ancient history into an ongoing event happening in real time, right now, while you listen to this. The Oort Cloud is so unimaginably far away that an object dislodged from it does not arrive quickly. Even falling under the pull of the sun's gravity, even accelerating the entire way inward, the journey from the outer Oort Cloud to the inner solar system takes an enormous span of time. hundreds of thousands of years in many cases, sometimes longer, which means the objects that were shaken loose 2.5 million years ago by that passing star are not finished arriving. They are still falling. Some of them are still, right now, tonight, somewhere out past the orbit of Neptune, tumbling slowly inward on trajectories that were set in motion before a member of your own species had learned to control fire. The event is ancient. Its consequences are current. That gap between when the cause happened and when the effects are still unfolding is one of the strangest and most quietly unsettling things about this entire story. The current best estimate is that the long-period comet flux we observe today, the actual measured rate at which fresh, dynamically new comets are entering our sky, is running at roughly twice the long-term steady-state rate the galactic tide alone would maintain. Twice the normal supply, right now, in the sky above you, tonight. Kaib's estimate for how long this elevated period lasts before the solar system settles back down to its ordinary baseline is another 5 to 10 million years. We are, in other words, not near the end of this. We are somewhere in the middle of a wave that started before humanity existed in its current form, and will not finish until long after any of us are gone. There is a second consequence buried in all of this, and it runs in a direction most people would not expect. It concerns not the comets arriving today, but our entire estimate of how much material actually exists out there in the first place. Here is the problem. Almost everything astronomers know about the total population of the Oort Cloud, the trillions of objects estimated to be sitting in that distant shell, is inferred indirectly backward from the rate at which comets are currently arriving. You cannot count the cloud directly, so you count what falls out of it, and you use the galactic tide's known, steady drainage rate to work backward toward an estimate of the total reservoir feeding that drainage. If the current arrival rate is inflated, running at twice the normal baseline because of a recent stellar disturbance, then any population estimate built on top of that inflated rate is also inflated, if the sky looks twice as busy as it normally would. And astronomers have been quietly assuming that busyness represents the ordinary, steady behavior of an enormous reservoir. Then the actual reservoir feeding that busyness is thinner than previously thought. A busier sky, in this specific and slightly counterintuitive sense, implies a smaller cloud, not a larger one. We may have been looking at the aftermath of a shower and mistaking it for the ordinary weather. Now, before this story tips too far into certainty, it deserves the same honesty its own authors gave it. This result is not settled, and Kaib and Raymond do not claim that it is. Look again at the title of their own paper. It says a potential signature, not a confirmed signature, not proof, a potential one. That word is not modesty for its own sake. It is doing real scientific work, and it is worth understanding exactly why. There is a specific mismatch buried inside their own analysis, one they do not hide. The orbits their simulation produces when they model the flyby at the distance that best explains the scrambling in the new comet population come out smaller, on average, than the orbits actually observed in the real sky. The model and the data do not line up cleanly on that particular measurement. It is not a fatal problem, but it is a real one, and any honest accounting of this research has to include it. The leading candidate explanation for that gap involves something almost delightfully mundane sitting next to something so dramatic. Comets are not inert lumps of ice. As they warm, even slightly, even at enormous distances from the sun, they begin to vent jets of gas and dust from their surface, driven by sunlight slowly sublimating frozen material into vapor. That venting acts like an extremely faint, extremely slow thruster. over long enough timescales. It can nudge a comet's orbit into a slightly tighter path than gravity alone would ever produce. That effect, called a non-gravitational force in the technical literature, may be enough to explain why the observed orbits run smaller than the pure gravitational simulation predicts. It may account for the difference entirely. It has not yet been demonstrated to do so. That gap remains open, honestly labelled and unresolved. And there is a named critic on the record, which is exactly the kind of detail a responsible telling of this story should not leave out. Simon Portuguese Zwart of Leiden Observatory in the Netherlands has publicly questioned how much statistical weight this conclusion can actually bear. His objection is not philosophical. It is technical, and it is precise. The team built their model Oort Cloud using a single simulation containing 1 million test particles. Portuguese Zwart has argued that a result this consequential deserves testing against something closer to 100 million particles run across multiple different randomized starting configurations. Because gravitational interactions among enormous numbers of bodies are inherently chaotic. Tiny differences in where you start a simulation can cascade into large, unpredictable differences in where that simulation ends up. Run the process only once, and there is a real risk that what you have actually measured is not the universe. It is your own initial conditions dressed up to look like a discovery. His stated assessment, close to verbatim, is that concluding we are living inside the tail end of an enhanced phase of a comet shower remains genuinely up for debate, and that this result could turn out to be a one-off, an artifact of a single simulation run rather than a real feature of our solar system's history. But it is worth being precise about what kind of criticism this actually is. He is not dismissing the work. He has also said, on the record, that he is glad the authors are exploring this question, and that understanding the Oort Cloud and its role in our local cosmic neighbourhood genuinely matters. That is a scientist saying the question being asked is exactly the right one, while the specific answer on offer is not yet nailed down tightly enough to treat as settled fact. So hold this finding the way it deserves to be held. The evidence is real. The method behind it is genuinely clever, elegant even, a way of extracting information about an invisible past event from the statistical fingerprints left behind in objects we can actually observe. The conclusion is plausible, consistent with two independent lines of evidence pointing in the same rough direction. And it is not yet proven in the way that a 5 sigma discovery in particle physics is proven. It is a strong, testable hypothesis, sitting exactly where good, honest, unfinished science sits. And it gets more serious from here, not less, because a completely separate team of researchers did not stop at asking whether the star came close enough to matter. They asked the far blunter, far more uncomfortable question sitting one step further down the chain. If HD 7977 really did pass through the Oort Cloud at that kind of distance, how many of the objects it dislodged were actually capable of reaching Earth? Part 5. The impact numbers. There is a specific discomfort that arrives when a scientific question stops being about the distant past and starts being about arithmetic that includes the word Earth. That is exactly the shift that happened when a second separate team of researchers picked up where Kaib and Raymond left off, and asked a question neither of the earlier papers had directly answered. If a star really did pass close enough to disturb the Oort Cloud, how many of the objects it knocked loose actually end up crossing paths with this planet? The paper appeared in the journal Scientific Reports. The authors are Zhao Sao of Tsinghua University, working alongside Avi Loeb and Morgan MacLeod at the Center for Astrophysics, a joint institution run by Harvard and the Smithsonian. This is not a fringe collaboration. This is exactly the kind of team whose work gets taken seriously across the field, which is part of why the numbers in this paper are worth sitting with carefully rather than rushing past. At the time they wrote it, the precise encounter distance for HD 7977 had not yet been narrowed down by the comet signature method we just walked through. So the authors did the responsible thing. Rather than guessing at a single number, they modelled 3 separate scenarios spanning the full range that was plausible at the time. A close pass at roughly 2300 astronomical units. A middle pass at roughly 6400 astronomical units. And a distant pass at roughly 12,400 astronomical units. In the closest scenario, the numbers are severe enough that they deserve to be stated plainly and without softening. Roughly 5 comets, each at least a kilometre across, are expected to strike Earth within 1 million years of the encounter. And at the upper end of that same close scenario, objects up to 2¼ kilometres across become expected essentially with certainty. Not possible. Expected. To understand how extreme that actually is, you need the comparison number. The ordinary background rate the solar system produces without any stellar interference at all. Over that same million-year window, under normal steady-state conditions, the largest impactor you would typically expect to see strike Earth comes in around 225 meters across. And the probability of anything reaching a full kilometre in that same window sits at only about 5%. 5 comets at kilometre scale in the closest scenario against a normal background where you would not expect even one. That is the shape of the difference a nearby stellar flyby can carve into the risk profile of an entire planet. Now, before that number sits in your mind as the headline, it needs an immediate and important correction, because 5 is not the scenario we actually appear to be living inside. Remember what Kaib and Raymond's comet signature method narrowed the encounter distance down to, not 2300 astronomical units, somewhere between 6,000 and 10,000. That range lands almost exactly on the middle scenario in this second paper, the 6400 astronomical unit model, not the closest, most catastrophic one. So the honest number, the one that best reflects our current understanding once both papers are read together rather than in isolation, is not 5-kilometre scale comets. It is 1 to 2. 1 or 2 kilometre scale comets striking Earth within 1 million years against a background expectation where you would ordinarily expect essentially none. The impact probability, even in this more moderate, more likely scenario, still rises by more than a full order of magnitude above normal. That is not a rounding error. That is the difference between an event so rare it barely registers in a species' entire recorded history and an event that becomes, for a geologically brief window, a genuine and elevated feature of what this planet has to survive. There is a further detail buried in the closest scenario that is worth mentioning, even though it is not the scenario we are most likely in, because it illustrates just how dramatically a passing star can restructure the actual hierarchy of threats a planet faces. In that closest pass model, the cometary impact rate does not just rise. It actually exceeds the background asteroid impact rate, the rate derived independently from studying crater counts on the Moon, which serves as a kind of undisturbed record of impacts across the inner solar system. For a stretch of time, in that scenario, comets would have become the primary threat to Earth, not the secondary one. Asteroids get most of the attention in modern planetary defense conversations, largely because their orbits are more predictable and easier to track. Long-period comets, arriving for the first time from the outer Oort Cloud on trajectories nobody has ever measured before, are a fundamentally harder problem, and for a window of time following a close stellar encounter, they can become the dominant one. And then the paper does something that moves this entire discussion out of pure modelling and into the geological record itself. It points at a timestamp. The modelled comet shower produced by this encounter, according to the simulations, peaks shortly after the 2.5 million year mark. That timing lands almost exactly on what geologists call the Pliocene-Pleistocene transition, one of the significant reorganizations in Earth's climate history. It marks the shift toward the recurring Ice Age cycles that would go on to shape the following 2.5 million years of the planet's climate, its landscapes, and eventually the entire evolutionary path of the genus that would become us. The authors are careful, and this is worth emphasizing, careful about exactly how they frame this connection. They are not claiming a single dramatic dinosaur extinction-style impact caused this climate shift. They argue instead that a sustained, elevated comet flux spread out gradually over hundreds of thousands of years rather than delivered in one catastrophic moment actually fits the observed character of that climate transition better than a single collision would. The Pliocene-Pleistocene shift was gradual. It unfolded over a long stretch of time, not in an instant. A prolonged elevated bombardment, rather than one dramatic strike, is a more natural match for that kind of slow, cumulative planetary change. They also point to a specific, real, physical piece of evidence sitting almost exactly inside that same window. The Eltanin impact, a known collision event in the South Pacific, dated close to that same boundary, produced by an object estimated at somewhere between 1 and 4 kilometers across. The prevailing explanation for Eltanin in the existing literature has generally been an asteroid. This paper offers cometary bombardment as a plausible alternative explanation, and it goes further, listing a small set of craters scattered across the planet whose ages cluster in roughly the right window. Elgy-Gitgin in Russia, 18 kilometers wide. Zamanshin in Kazakhstan, 14 kilometers wide. Bosom Twi in Ghana, 10.5 kilometers wide. All three implying impactors in that same 1 to 2 kilometer range the model predicts. But here is where the paper's own restraint becomes the most important part of the entire story, and it is worth stating with exactly the same care the authors used, because this is the difference between careful science and a dramatic voiceover. Crater ages carry large uncertainties. Dating an impact crater precisely enough to line it up against a 2.5 million year old astronomical event is genuinely difficult, and the error bars involved are often wide enough to make a clean match uncertain rather than confirmed. Most impacts, historically, leave no recoverable record at all because roughly 70% of Earth's surface is ocean, and craters that land in deep water are erased, buried, or simply never found. On land, erosion and sediment slowly erase the evidence over exactly the kind of timescales involved here. Telling a cometary crater apart from an asteroidal one purely from the physical evidence left behind on the ground is genuinely difficult, often close to impossible with current techniques. And some comets, particularly smaller or more fragile ones, break apart entirely in the atmosphere before ever reaching the surface, leaving no crater whatsoever, no matter how large the original object was. The author's own conclusion, stated plainly rather than dressed up, is that the shower could have been a contributing factor to the Pliocene-Pleistocene transition, not the cause, a contributing factor. That distinction is the entire difference between responsible science and sensationalism, and it is worth carrying with you as the true shape of the threat in this story, because it is worth being precise here at the center of all of this about exactly what kind of threat we are actually talking about. Nothing is inbound. No object identified by either of these papers is on a collision course with Earth. Nothing in either study changes your risk this year or next year or across the next 1,000 years of ordinary human timescales. What has changed, what these two papers together genuinely establish, is something quieter and in some ways stranger. The comet hazard facing this planet is not a fixed, unchanging property of the solar system, a constant background hum you can simply forget about once you have learned the baseline number. It is a variable, and it is a variable that an outside object, a star passing through territory that does not belong to it, can raise by a factor of 10. And it was raised, and we are still, right now, tonight, living somewhere downstream of that increase, inside a wave that has not yet finished passing through. Part 6. Not the only one. If HD 7977 were a singular event, a one-time anomaly in the entire multi-billion-year history of the solar system, it would still be a remarkable story. A star reaching into our territory once, in the entire span of time since the sun ignited, would be worth telling on its own. It is not a singular event. It is not even the only one we know about with confidence. And that fact, more than any single number in either paper, is the part of this story that should genuinely follow you into sleep tonight. 70,000 years ago, recently enough that anatomically modern humans were already here, already walking, already capable in principle of looking up and seeing whatever there was to see. A dim binary star system, now known as Schultz's star, passed within roughly 52,000 astronomical units of the Sun. Convert that into more familiar units, and you get roughly a quarter of a parsec, or about 0.8 light years. That is still, to this day, the closest known stellar encounter with well-constrained distance and velocity in the entire scientific literature. It was established in a paper published in 2015 by Eric Mamajek and colleagues, carrying a title that does not try to dress up what it found. The straightforward closest known flyby of a star to the solar system. Schultz's star passed through the outer reaches of the Oort Cloud, further out than HD 7977's much more recent and much closer intrusion, but real, confirmed, and measured. And here is the detail that should sit uncomfortably alongside everything you have just heard about the current comet wave. Whatever Schultz's star knocked loose 70,000 years ago is, in all likelihood, still falling. At the distances involved, the travel time inward from the outer Oort cloud runs to 1,000,000 years or more, which means the consequences of an event that happened while modern humans were already alive on this planet, watching the same night sky you are imagining right now, will not fully arrive for roughly another 1,000,000 years. We are not waiting for those results. Nobody currently alive will ever see them. Some almost unimaginably distant version of whatever our descendants become might. Sit with that for a moment before we move forward, because it reframes the entire scale of what is actually happening here. This is not a single freak coincidence involving one star, one solar system, one improbable near miss. This is a process. A slow, recurring, statistically expected feature of how a star embedded in a spiral galaxy actually behaves over cosmic timescales. Stars pass close to other stars. Not often, on any timescale a human mind finds intuitive, but often enough across the true age of a solar system that it becomes a predictable, quantifiable part of that system's history rather than an exception to it. And there is one more piece of this, the piece that turns this story from something entirely about the past into something with a genuine, calculable, present tense edge to it. Because there is a star already measured, already tracked, already on a trajectory that carries it toward us rather than away, and it is coming the other direction across time. Not something that already happened, something that is going to happen. It is a K-type orange dwarf, smaller and cooler than our own Sun, sitting roughly 63 light-years away in the constellation Serpens. It carries the catalogue designation Gliese 710. And according to current measurements, it is on track to make the closest known future stellar approach to our solar system, arriving at its closest point roughly 1.28 million years from now. Some analyses place its closest approach as near as roughly 5,200 astronomical units from the Sun. Read that number back against everything you have just spent the last several minutes absorbing. 5,200 astronomical units would place Gliese 710's future encounter closer than HD 7977 ever came to us. Closer than the 6,000 to 10,000 astronomical unit range that the comet signature method identified for the star responsible for the wave we are living inside right now. It would sit below the roughly 7,000 astronomical unit threshold that the impact modelling identifies as the point where the odds of a kilometre-scale comet strike spread across the following million years. Cross from merely elevated into essentially certain. It is currently considered essentially certain, not merely likely, that Gliese 710 will pass directly through our Oort cloud. And there is a detail attached to this prediction that deserves to be said plainly, because it says something important about the direction our understanding of this threat has been moving. Earlier measurements of this star's motion, made using an older European mission called Hipparcos, had placed its future closest approach considerably farther out than we now believe. When Gaia's far more precise measurements came in, they moved the predicted encounter distance roughly 5 times closer than the older data had suggested. Better instruments made the future look more dangerous, not less. That is worth sitting with on its own. This is not a case where improving our data has calmed a previously alarming prediction. It is a case where improving our data sharpened a prediction that was already concerning into something considerably closer to certain. There is one additional idea attached to Gliese 710 worth mentioning here, clearly labelled for exactly what it is: speculation, not a finding of either paper we have discussed tonight. A close stellar passage does something unusual to the practical geometry of interstellar distance. It temporarily places another entire star system within a dramatically shorter travel distance than it would occupy under ordinary circumstances for as long as the encounter lasts. Some researchers, working well outside the specific comet studies at the centre of this story, have floated the idea that a sufficiently advanced civilization, somewhere at some point in cosmic history, might treat an encounter like this as a kind of low-energy stepping stone. Rather than expending the enormous energy required to cross an ordinary interstellar gap, you simply wait. You let the star come to you across the ordinary, patient drift of galactic motion and make your crossing during the brief window when the distance involved is dramatically smaller than usual. Whether Gliese 710 has any planets at all orbiting it remains genuinely unknown at the time of this recording. File that particular idea exactly where it belongs, under interesting rather than established, a genuinely fascinating thought experiment rather than a scientific claim with any evidentiary weight behind it. And none of it, is actually rare on the true timescale a solar system experiences. This is perhaps the single most important reframing this entire story has to offer. Statistical estimates, built from Gaia's extraordinarily precise census of the galaxy's stellar population, put the number of stellar encounters within roughly a light and a half of the Sun at something like 12,000 across the full history of the solar system. 12,000 separate approaches, close enough to potentially matter, scattered across 4.5 billion years. Gaia's data alone has already identified 25 individual stars that are known to have passed within 3 light years of us. And this is not a phenomenon unique to our own solar system, observed only through the indirect fingerprint of scrambled comet orbits. Astronomers have directly watched stellar flybys disturb the disk of material surrounding other distant stars, in systems where the disturbed material can actually be imaged and studied in real time. That direct observational confirmation matters enormously, because it means the mechanism at the center of this entire story is not some clever bookkeeping trick invented specifically to explain an odd pattern in our own comet catalogue. It is something stars, ordinary stars, embedded in an ordinary spiral galaxy, simply do to each other repeatedly as a routine feature of how a galaxy actually behaves over deep time. We have been treating the solar system, in the popular imagination, as something close to a sealed room, a closed system, its planets and comets and asteroids all quietly obeying their own internal rules, largely insulated from whatever else is happening in the wider galaxy around it. That picture was always convenient. It was never entirely true. And the deeper you look into the actual statistics of stellar motion across galactic time, the less true it becomes. The room has a door. The door opens more often than anyone comfortably assumed, and something, quite recently, walked through it. Part 7. The instrument that will settle it. Every story like this one eventually arrives at a moment where the interesting thing is not what we already know, but what we are about to find out. That moment, for this particular story, is not abstract or distant. It has a date attached to it, and that date is close enough to matter to anyone listening tonight. In December, the Gaia mission is scheduled to release its next major batch of data. This is not a routine, incremental update. Each Gaia data release represents a meaningful leap in precision over the one before it because the spacecraft's entire method depends on accumulating time. The longer Gaia watches a star, the more precisely it can measure that star's motion across the sky. And the more precisely it can measure that motion, the more confidently astronomers can run the clock backward or forward and calculate exactly where that star has been, or exactly where it is going. For HD 7977 specifically, this next release matters enormously, because it will sharpen the star's trajectory on both ends of the question that has defined this entire story. How close did it actually come? And precisely when did that closest approach occur? Right now, both of those numbers carry meaningful uncertainty, wide enough that the entire severity of the encounter still sits somewhere on a spectrum rather than pinned to a single confirmed value. And here is why that particular piece of incoming data matters so much more than an ordinary scientific update usually would. Because the impact numbers in the second paper we discussed, the ones built by Sao, Loeb and MacLeod, do not scale gently with encounter distance. They scale steeply. The difference between a closest approach of 2,300 astronomical units and one of 12,400 astronomical units is not a modest adjustment to the final numbers. It is the difference between 5-kilometer scale comets striking Earth within 1 million years and essentially none at all. A relatively modest revision to the encounter distance, in either direction, has the power to meaningfully shift this entire conversation. If the refined trajectory that arrives in December comes in nearer than roughly 6,000 astronomical units, the more severe scenario, the one closer to 5-kilometer scale impacts rather than 1 or 2, moves back onto the table as the more likely outcome. If the refined distance instead comes in farther out than the current estimate, the entire comet shower interpretation weakens considerably, and this story shifts back toward being a genuinely fascinating but ultimately survivable footnote in the solar system's recent history, rather than an ongoing, elevated hazard we are currently living inside. That is the honest position science is in right now, tonight, as you are hearing this. Not a settled conclusion. A hypothesis, built from two independent and genuinely clever lines of evidence, sitting directly in the path of a specific, datable test that is going to arrive within the next several months. There is a second instrument entering this story as well, one whose relevance goes far beyond simply refining a single star's trajectory. The Vera C. Rubin Observatory, a new ground-based survey telescope, began its full operational sky survey recently, and it represents something genuinely different from almost everything that has come before it. Rubin is designed to photograph the entire visible sky repeatedly across an extraordinarily wide field of view with a sensitivity to faint, distant, slow-moving objects that no previous survey has been capable of matching. What makes this relevant to everything we have discussed tonight is almost embarrassingly direct. Rubin is expected to detect faint, extremely distant solar system objects that no earlier instrument could ever have picked out of the darkness, potentially including bodies sitting within the inner Oort Cloud itself, the closer, somewhat flattened portion of that vast shell we described earlier, the part that begins at roughly 2,000 astronomical units and extends outward from there. If Rubin manages to do that, it will represent something genuinely unprecedented. The first direct observational handle on a population that up to this point humanity has only ever understood indirectly, through theory, through simulation, through the second-hand fingerprints left behind in the handful of comets that happen to fall inward and become visible. Everything we have discussed tonight about the size of the Oort Cloud, the total number of objects it contains, the population estimates running into the trillions, all of it has been inference, educated, careful, mathematically rigorous inference, but inference nonetheless, built from indirect evidence rather than direct observation. If Rubin can begin to actually count what is genuinely out there rather than estimating it backward from arrival rates that we now suspect may themselves be temporarily inflated by a recent stellar disturbance, the entire argument stops being an inference chain built on inference chains. It becomes a measurement. And a measurement, however difficult to obtain, carries a different kind of scientific weight entirely. It would let researchers directly test whether the Oort Cloud really is smaller than previously assumed, exactly as the elevated arrival rate would predict if the current comet shower interpretation holds. It would let them directly compare the actual population against the models built from HD 7977's suspected passage, rather than comparing one set of assumptions against another. We are, in other words, standing at a genuinely rare moment in this particular corner of astronomy. A hypothesis has been proposed. Two independent methods have converged on roughly the same rough answer. A named, credentialed critic has raised a specific, technically valid concern about the statistical foundation underneath it. And two separate, real instruments, one refining an old measurement, one attempting an entirely new kind of measurement, are both scheduled to weigh in within a time frame short enough that you, personally, listening to this tonight, may well be alive to hear the resolution. That is not always true of the mysteries this genre of documentary tends to explore. So often, the open questions in physics and cosmology stretch across timescales so vast that resolution feels permanently, comfortably out of reach, safely distant from anyone currently alive. This one does not have that luxury, or perhaps that comfort. This one has a date. December is coming. And whatever Gaia's next data release actually shows, whatever number falls out of that refined trajectory, it will not erase the underlying reality this story has already established. A star did come through. The comets in our sky right now are not simply the ordinary background hum of a quiet, undisturbed solar system. They are, at least in part, the visible tail of a wave. And the source of that wave has already been found, catalogued, and is still sitting out there in Cassiopeia, 250 light years away. Exactly where you could look for it tonight if the sky happened to be clear. Part 8. What it would actually look like. It is worth pausing here in the middle of all this data and all these distances to ask a simpler and more human question. What would any of this actually look like if you were standing on the ground watching it happen? The answer is almost anticlimactic, and that anticlimax is itself part of what makes this story strange. HD 7977's passage through the outer Oort Cloud 2.5 million years ago would have produced nothing visible in the sky at all. No flash, no warning light, no slow, dramatic brightening of a strange new star creeping closer over the course of a human lifetime. At the distances involved, thousands of astronomical units. Even a star passing directly through your solar system's outer territory remains an unremarkable point of light, if it is visible to the naked eye at all. The event that reshaped the comet population of an entire solar system that may have contributed to a genuine shift in Earth's climate happened in complete silence, invisible to anything alive at the time to witness it. That is worth sitting with because it cuts against almost every instinct you have about how a threat of this scale should announce itself. You expect danger to look dangerous. You expect a star reaching into your solar system to look, at minimum, like something. It does not. The entire mechanism unfolds in the dark, over distances so vast that even light itself takes months to cross them, acting on objects so small and so far away that no naked eye, ancient or modern, would ever have caught it happening. What would have been visible eventually, hundreds of thousands of years later, once the wave of dislodged comets began arriving, is something closer to what you might expect from an ordinary night sky, just more frequent than usual. Long-period comets, the rare, spectacular visitors that occasionally sweep close enough to the sun to grow a visible tail, streaming inwards slightly more often than the normal background rate would produce. Not a storm, not a visible bombardment, just an elevated frequency of an event that already happens on its own, spread out gently enough and slowly enough that no single observer across any single human lifetime would necessarily have noticed the difference between an ordinary comet year and an elevated one. This is part of why the case for a connection to the Pliocene-Pleistocene transition rests on statistics and geology rather than on any dramatic, single, memorable event. There was, as far as the evidence currently shows, no equivalent of the object that struck the Yucatan Peninsula 66 million years ago, the strike widely understood to have ended the age of the non-avian dinosaurs. That object is estimated at somewhere around 10 kilometers across, a single, sudden, catastrophic impact whose effects unfolded within years, not millennia. Nothing in either of the papers we have discussed tonight suggests anything of that scale occurred during this comet shower. The elevated impact rate identified here involves objects in the 1 to 2 kilometer range, arriving not as a single strike, but scattered across hundreds of thousands of years. Serious, genuinely elevated above the ordinary background rate, but categorically different in both scale and pace from the kind of event capable of ending an entire geological era in a single afternoon. It helps here to actually understand what an object in that 1 to 2 kilometer range is capable of doing, because the phrase kilometer scale comet can sound almost abstract until you attach real consequences to it. An impact from an object of that size striking anywhere on Earth's surface would release energy on a scale measured not in the ordinary vocabulary of explosions, but in the vocabulary geologists reserve for planetary events. The immediate blast would obliterate everything within a wide radius of the impact site, and the secondary effects, the shockwave. The ejected material thrown high into the atmosphere, the potential for tsunamis if the strike occurred in an ocean, which, given how much of Earth's surface is ocean, is the statistically likely outcome, would extend the damage far beyond the crater itself. Dust and debris lofted into the upper atmosphere could dim sunlight across the globe for a period of months, disrupting plant growth, disrupting the base of entire food chains in a milder, more survivable echo of the far more catastrophic effects associated with the extinction-level impact that ended the age of dinosaurs. None of that happened as a single event in this story. What the evidence suggests instead is something closer to a slow drumbeat, a handful of such impacts spread across hundreds of thousands of years, layered on top of an Earth that was already, for entirely separate and well-understood reasons involving shifting ocean currents and changing continental configurations, sliding toward a colder, more variable climate regime. The comet shower, in the framing these researchers offer, is not the cause of the ice ages. It is, at most, one additional pressure applied at roughly the same time. One more disruptive input layered onto a planet that was already in the middle of reorganizing itself. There is something almost humbling in that framing, if you let yourself sit with it. We tend to imagine planetary scale change as requiring a single, dramatic, identifiable cause. One asteroid, one eruption, one clean line you can draw on a timeline and say, here, this is where everything changed. The reality, in this case as in so many others across Earth's deep history, appears to be messier and more layered than that. Multiple slow pressures arriving from entirely different directions, some geological, some astronomical, compounding on top of each other across a span of time too long for any single cause to stand out cleanly against the noise. And this is, in its own way, part of what makes the ongoing nature of this particular wave so quietly strange to think about as you lie there tonight. We are, right now, according to the best current estimate, living inside a version of that same elevated period, not the peak of it. The peak, according to the modelling, occurred closer to the actual moment of the encounter, hundreds of thousands of years after HD 7977 passed through, as the bulk of the dislodged material had time to fall inward. We are somewhere further along the tail of that wave, still elevated above baseline, according to the current estimate running at roughly twice the normal long-term rate, but past the most severe portion of it, gradually easing back toward the ordinary background hum that governed the solar system before this star ever arrived. That easing is expected to continue for another 5 to 10 million years before the system fully settles, which means that every generation of humans who has ever lived, every civilization that has ever risen and fallen, every single recorded moment of human history has existed entirely within this elevated window, without anyone knowing it, without anyone being able to know it, until a spacecraft designed to map stars, not comets, happened to notice a trajectory that led straight back toward us. That is the quiet, strange gift buried inside this entire story. Not that we are in danger, in any way that should keep you from sleeping tonight. We are not. Nothing is inbound. No object has been identified on any path toward this planet as a result of either paper we have discussed. What has changed is something more subtle and, in its own way, more remarkable. We now know something about the texture of the sky above us that no generation before us ever had access to. We know that the comets streaking silently across the night, the ones people have watched with wonder for the entire span of recorded history, are not simply random, isolated visitors from an eternal, unchanging background. Some meaningful fraction of them are messengers. Evidence, the visible tail end of something that reached into our solar system before any of us existed, and is still, quietly, gradually, finishing the job it started. Part 9. The critics and why they matter. It would be easy at this point in the story to let the momentum carry you forward without pausing on the people pushing back against it. That would be a disservice, both to the science and to you, because the disagreement sitting inside this research is not a minor footnote. It is one of the most important parts of the entire story, and understanding it properly is what separates a genuinely informed listener from someone who has simply absorbed a dramatic headline. Science does not typically move forward through single, clean, unanimous discoveries. It moves through exactly this kind of friction. A claim is made. Someone with the technical standing to evaluate it properly pushes back, not out of stubbornness or contrarianism, but because the specific methodology used to reach the claim has a specific, identifiable weakness that deserves to be tested before the result is treated as established fact. That is not science failing. That is science working exactly as it is supposed to work. Simon Portuguese-Zwart's objection, the one we touched on earlier, deserves a fuller hearing here, because the reasoning behind it illuminates something important about how difficult this entire category of research actually is. His core concern is about the number of particles used in the Oort Cloud simulation, and about the fact that only a single realization of that simulation was run. To understand why that matters, you have to understand something fundamental about how gravitational simulations of large chaotic systems actually behave. When you are modeling a system as complex as a simulated Oort cloud, containing objects whose orbits are influenced by the Sun, by the giant planets, by the galactic tide, and now, additionally, by a passing star, you are modeling what is technically known as a chaotic system. In a chaotic system, tiny differences in the starting conditions, differences so small they would seem completely irrelevant on their own, can cascade over time into dramatically different final outcomes. This is the same underlying mathematical principle behind the popular idea of the butterfly effect in weather prediction. Run the same basic physical setup twice, with only the smallest possible difference in the starting positions or velocities of the particles involved, and after enough time has passed, the two simulations can diverge into results that look nothing alike. Kaib and Raymond's model used a single Oort cloud realization built from 1 million individual test particles, run forward once with the stellar flyby included. Portuguese-Zwart's argument is that a result this consequential, one that potentially reshapes our understanding of Earth's recent impact history and the true size of the Oort cloud itself, deserves to be tested against many independent realizations, ideally with a far larger particle count, before its specific conclusions are treated as reliable. Run the simulation 100 times, with 100 slightly different starting configurations, and see whether the same basic pattern, the same scrambling of new comet orbits, reliably emerges every time, or whether it only appears under the particular set of starting conditions this one team happened to choose. This is not an unreasonable standard to apply. It is, in many corners of computational astrophysics, the expected standard. And it is worth being honest about the fact that Kaib and Raymond's own paper does not claim to have met it. They built one model. It matched the observed data reasonably well, with one identified area of mismatch, the orbit size discrepancy we discussed earlier. That is a meaningful, genuinely interesting result. It is not, on its own, the kind of exhaustive statistical validation that would let a result like this graduate from hypothesis to established scientific consensus. There is a broader lesson buried inside this specific disagreement, one that extends well beyond this particular pair of papers, and it is worth carrying with you as a kind of general tool for evaluating any dramatic scientific claim you encounter, in this documentary or anywhere else. The existence of a plausible mechanism, a clever method, and a result that matches observed data reasonably well is genuinely exciting, and it is genuinely worth reporting on. It is not, by itself, proof in fields dealing with genuinely chaotic, genuinely uncertain systems like this one, requires exactly the kind of repeated, varied, statistically robust testing that Portuguese Oort is calling for. Testing that takes real time, real computational resources, and real scientific patience to complete properly. This is also, it is worth saying clearly, precisely why the December Gaia data release and the ongoing Rubin Observatory survey matter so much more than they might if this were already a fully settled question. They represent exactly the kind of independent external validation this research still needs. Not a rerun of the same simulation with slightly different starting numbers, which is useful but limited, but genuinely new, independent observational data, capable of testing the underlying hypothesis against reality itself rather than against another layer of modelling. There is something worth appreciating in how this disagreement has actually played out publicly, something that runs counter to how scientific disputes are often portrayed. Portuguese Oort did not dismiss the work. He did not accuse the authors of overreach or sloppy science. His stated position, again close to verbatim, was that he was glad the authors were exploring this question, that understanding the Oort Cloud and its role in our local cosmic environment genuinely matters, and that the specific conclusion that we are currently living inside the tail end of an enhanced comet shower remains up for debate rather than settled. That is a remarkably generous, remarkably constructive form of scientific disagreement. It is not two camps at war with each other. It is one group proposing a genuinely clever, genuinely testable idea, and another respected researcher in the same field saying, essentially, I believe this deserves more rigorous testing before we treat it as fact, and I am glad someone is doing the work to find out. That is worth remembering the next time you see a headline built from a single new paper in any field presented as settled, final truth. The actual texture of science almost always looks much more like this. A genuinely interesting idea, built on real evidence, sitting inside an active, ongoing, good faith disagreement about exactly how much weight that evidence can currently bear. The headline version flattens all of that texture into a single, confident claim. The reality is messier, slower, and in its own way considerably more interesting, because it means the story is not actually finished. It means you, listening to this tonight, are hearing about a genuine, live, unresolved question in modern astronomy. One that a specific datable piece of new evidence is going to meaningfully move one way or the other within the next several months. There is one more layer worth adding here, because it rounds out the picture of exactly how seriously this idea is being taken across the field, beyond the two teams directly responsible for it. The broader concept of stellar flybys disturbing the Oort Cloud and elevating the comet impact rate on Earth is not, in itself, a new or fringe idea. It has circulated in the scientific literature for decades, in various forms, tied to various other proposed close stellar encounters throughout Earth's deep history. What makes the HD 7977 case different? What has actually elevated it into serious, ongoing discussion, rather than leaving it as one more entry on a long list of speculative historical near misses, is the unusually tight convergence between two genuinely independent lines of evidence. The Gaia-derived trajectory of the star itself, run backward through time, and the statistical fingerprint identified in the actual, currently observed population of long-period comets. Two separate methods, built on two separate datasets, both pointing toward the same rough region of space and time. That convergence is precisely why this particular case has generated the level of attention it has, even while the specific details, the exact distance, the exact severity, the exact connection to Earth's climate history, remain genuinely, actively unresolved. Part 10. What we still don't know about our own backyard. There is a particular kind of humility built into this entire story, one that becomes clearer the longer you sit with it, and it has less to do with stars 250 light-years away than it does with something far closer, sitting quietly in the same solar system you have called home your entire life. We have spent this whole documentary talking about the Oort Cloud as though it were a well-characterized, well-understood object. A shell whose properties we can describe with confidence, whose population we can estimate in the trillions, whose structure we can divide neatly into an inner disk-like region and an outer spherical one. All of that is true, in the sense that it represents the genuine, careful, best current understanding of serious researchers working in this field. It is also worth remembering, plainly and without qualification, that not one single object in that entire vast reservoir has ever been directly observed. Not one. Every single number attached to the Oort Cloud, its total population, its inner and outer boundaries, its overall mass, is a theoretical construct built from models calibrated against the small trickle of comets that happen to fall inward and become visible to us. This is an almost uniquely strange situation in modern astronomy. We routinely photograph galaxies so distant that their light left them before the Earth itself had finished forming. We have detected gravitational waves rippling outward from black hole collisions that occurred over 1 billion light-years away. We have mapped the faint, ancient afterglow of the earliest light in the universe, dating back nearly to the beginning of time itself. And yet, the nearest, most local reservoir of material, still gravitationally bound to our own star, sitting at the very edge of what we can technically call our own solar system, remains almost entirely invisible to us, known only through inference and indirect evidence. That gap between our confident knowledge of the extremely distant universe and our genuinely uncertain knowledge of our own solar system's outer edge is worth sitting with. It is not a failure of ambition or effort. It is simply a consequence of physics. Distant galaxies are enormous and, in astronomical terms, extraordinarily bright, radiating light across vast stretches of the electromagnetic spectrum. Objects in the Oort Cloud are small, cold, and reflect only the faintest trace of sunlight at a distance where the sun itself has dimmed to something barely brighter than an ordinary distant star. Brightness and size make distant galaxies easy, relatively speaking, to see. Faintness and proximity to nothing at all make our own outer solar system extraordinarily difficult to see, despite being, on any absolute cosmic scale, right next door. This is precisely why the Vera Rubin Observatory's ongoing survey carries the significance it does. Well beyond its specific relevance to this particular story about HD 7977, Rubin represents a genuine leap forward in exactly the kind of sensitivity required to finally begin closing this gap, to start directly detecting faint, slow-moving objects at the very edge of what our own solar system actually contains, rather than continuing to infer their existence indirectly, one comet at a time, from the objects that happen to fall inward and become visible on their own. There is something worth appreciating in the fact that this particular gap in our knowledge, the uncertain size and structure of our own Oort cloud, is precisely the gap that makes a story like the HD 7977 encounter simultaneously so compelling and so difficult to fully resolve. If we already had a precise, direct census of every object in the Oort cloud, this entire investigation would look completely different. Researchers would simply be able to compare the actual directly observed population against the predicted effects of a stellar flyby, and the question would resolve itself relatively quickly and cleanly. Instead, because we are working almost entirely from indirect evidence, from the statistical fingerprints buried in a few hundred comet orbits, from population estimates built on models rather than direct counts, every step of this investigation has to proceed carefully, cautiously, with appropriate uncertainty attached to each individual conclusion. That caution is not a weakness in the story. It is, in a very real sense, the most honest and scientifically appropriate response available to the genuine limits of what we currently know. It would be far easier and far more dramatic to simply declare that a comet shower struck Earth 2.5 million years ago and reshaped its climate, full stop, no qualifications attached. It would also be considerably less true to the actual state of the evidence. The real, careful version of the story, the version these researchers themselves have offered, is more modest and, in its own way, more genuinely interesting. A star came close. The comets in our sky carry a fingerprint consistent with that encounter. The timing lines up suggestively, though not conclusively, with a known shift in Earth's climate history. And multiple pieces of new evidence, arriving within the next several months to next few years, stand a genuine chance of either strengthening or substantially weakening this entire picture. There is a particular kind of intellectual pleasure available in sitting with a genuinely unresolved question like this one, rather than rushing toward a tidy false certainty in either direction. It would be easy to round this story off into pure alarm, treating the elevated comet flux as an imminent, ongoing danger deserving of genuine anxiety. It would be equally easy and equally dishonest to round it off in the opposite direction, dismissing the entire finding as unproven speculation not worth taking seriously at all. The genuinely honest position sits somewhere in the careful middle ground between those two extremes, and holding that middle ground, resisting the pull toward either false comfort or false alarm, is itself a kind of intellectual discipline worth practicing, here and in how you evaluate scientific claims more broadly, long after this particular story fades from the headlines. What remains true, regardless of how the December data release ultimately resolves the specific numbers, is that this entire investigation has already changed something real about how we understand our place in the galaxy. Before this research, the prevailing intuitive picture, even among many people who consider themselves reasonably well informed about space, treated the solar system as a largely closed, self-contained system. The Sun, the planets, the asteroid belt, the distant Kuiper belt, all operating according to their own internal, largely undisturbed rhythms, quietly insulated from the wider churn of the galaxy beyond. That picture we now understand with real confidence. However uncertain the specific details of this particular encounter remain, was always incomplete. The door to our solar system opens more often than that comfortable picture ever allowed for. Something walked through it recently. Something else is scheduled to walk through it again, in roughly 1,000,000 years, arriving closer than the last visitor did. Part 11. Deep Time and the Strangeness of a Schedule. There is something genuinely unusual about being able to say, with real scientific confidence, that we know roughly when the next close stellar encounter is going to happen. Most of the mysteries explored across long-form documentaries like this one exist entirely in the deep, comfortable safety of either the distant past or the effectively infinite future, so far removed from any human timescale that they carry no real weight in your own life, tonight, as you listen. This story does not offer quite that same comfortable distance, and it is worth sitting with exactly why. Gliese 710's approach, roughly 1.28 million years from now, is not something any human being currently alive, or any human being whose descendants we can meaningfully imagine, will ever witness. 1,000,000 years is a genuinely vast stretch of time on any human scale. It exceeds the entire history of anatomically modern humans several times over. It is longer than the time separating you from the era when Homo erectus was walking the same Earth that HD 7977's passage occurred within. Whatever form our species, or whatever we eventually become, takes by the time Gliese 710 arrives, it will very likely be as unrecognizable to you as you would be to whatever walked the Earth 1,000,000 years before you were born. And yet there is something quietly remarkable in the fact that we can say anything at all with genuine confidence about an event that far removed from the present moment. Human beings have spent the vast majority of their history essentially blind to the deep future, capable of predicting the weather a few days out at best. Capable of predicting the return of a comet a century in advance if they were unusually skilled and patient, but genuinely incapable, for the overwhelming majority of human history, of saying anything meaningful about events over 1,000,000 years away. That capability, the ability to look at a star 63 light-years distant, measure its precise motion with instruments sensitive enough to detect movements smaller than the width of a human hair seen from a mile away, and calculate its position more than 1,000,000 years into the future, did not exist in any meaningful form until extraordinarily recently. It is, in the fullest sense, a genuinely new kind of knowledge, one that previous generations of human beings, across the entire span of recorded history, simply did not have access to. There is a strange kind of vertigo built into holding that knowledge, and it is worth naming clearly, because it is part of what makes a story like this one different from most of the deep time mysteries this genre typically explores. You are not simply learning about something that happened, safely sealed away in the unchangeable past. You are learning about something that is, in a genuine, calculable sense, still scheduled, still coming. Not soon, not in any way that should keep you from sleeping tonight, but real. In a way that a story about, say, the eventual heat death of the universe, trillions of years distant, somehow does not quite manage to be. 1,000,000 years feels, paradoxically, close enough to imagine and distant enough to remain entirely abstract, both at once. Consider, for a moment, what has actually changed on Earth across the roughly 2.5 million years since HD 7977's own passage, because it offers a genuine, tangible sense of scale for what a similar stretch of time might hold before Gliese 710's arrival. 2.5 million years ago, the genus Homo had only just begun to emerge as a distinct branch on the evolutionary tree. The tools our ancestors used were simple, unworked stones, barely modified from their natural state. There was no agriculture, no writing, no cities, no science capable of measuring the motion of a distant star. Every single technological, cultural and biological development that separates you from that distant ancestor happened entirely within the span of time that has passed since that star made its quiet, invisible passage through our Oort Cloud. Project that same span of transformation forward, and you begin to grasp just how genuinely unknowable the world awaiting Gliese 710's arrival actually is. Whatever exists on Earth, or whatever remains of Earth, or whatever has replaced the concept of remaining on Earth entirely in 1.28 million years, will very likely bear as little resemblance to the world you know tonight as your world bears to the one HD 7977 passed through. And yet the star itself, the physics governing its motion, the mathematics capable of predicting its trajectory, none of that particularly cares about any of the transformation happening on the small, quiet planet it is slowly, patiently approaching. Gravity does not pause for civilizations to rise and fall. It simply continues, indifferent, precise, entirely unbothered by whatever is or is not watching from below. There is something worth holding on to in that indifference, something closer to comfort than dread if you let yourself sit with it the right way. The vast majority of stellar encounters across the true history of a solar system, the 12,000 or so estimated close passages across the Sun's 4.5 billion year lifetime, have left no meaningful trace at all. Most stars pass by too distantly to matter, disturbing nothing, dislodging nothing, leaving the Oort Cloud entirely undisturbed in their wake. HD 7977 appears to be a genuine exception, a close enough pass to leave a measurable fingerprint. Gliese 710, based on current projections, may prove to be another. But exceptions, by definition, remain rare, scattered thinly across spans of time too vast for any single perspective, human or otherwise, to fully absorb. And even in the case of a genuine confirmed close encounter, even in the most severe scenario modelled by either paper discussed tonight, the actual physical consequence for a planet like Earth remains survivable. Not without cost. Not without genuine elevated risk spread across hundreds of thousands of years. But survivable in exactly the sense that Earth itself and the long, unbroken chain of life that eventually produced you has already survived one such encounter, quietly, without a single mass extinction event marking its passage in the fossil record. The geological evidence, careful and thorough as it has been across more than a century of study, shows no catastrophic die-off correlated with the Pliocene-Pleistocene transition. Climate shifted. Ice ages began their long recurring cycle. Species adapted. Some thrived, some declined in the ordinary, gradual way that Earth's biosphere has always responded to gradual environmental change. Nothing about that transition looks like the sudden, violent signature of a true mass extinction event. That is, in its own quiet way, the most reassuring fact buried inside this entire story. We appear to have already lived through a version of exactly the kind of event we are describing tonight, an elevated comet flux, sustained across hundreds of thousands of years, contributing, at most, to an already unfolding climate transition, and the result was not catastrophe. It was simply one more thread woven into the already complicated, already gradual story of how this planet's climate and its life have continued adapting to each other across timescales too long for any single observer to have ever noticed the difference. Part 12. What the sky is actually telling you. There is a particular way of looking at the night sky that changes permanently once you have absorbed a story like this one. Not dramatically, not in a way that turns an ordinary evening walk into something anxious or fearful, something quieter than that. A shift in what the darkness actually represents. Before tonight, you might have looked up and seen something close to a fixed backdrop. Familiar constellations, tracing the same shapes they have traced for as long as human beings have bothered to name them. A handful of planets wandering slowly against that fixed backdrop according to their own steady, predictable rhythms. And, occasionally, if you were lucky, a comet streaking silently across the frame, rare enough to feel like an event, ordinary enough to be explained away as simply one more piece of the solar system's normal background behavior. What this story actually reveals is that the backdrop itself is not as fixed as it appears. Every star you can see, including the faint, unremarkable point of light sitting in Cassiopeia that carries the catalogue number HD 7977, is moving, drifting through the galaxy on its own trajectory, indifferent to the small, quiet planet whose comet population it apparently reshaped on its way past. Most of that movement means nothing to you, will never mean anything to you. Will simply continue for the entire remaining lifetime of the galaxy without ever intersecting meaningfully with anything happening on Earth. But some small fraction of it does intersect, rarely, unpredictably from any single human vantage point, but not unpredictably from the vantage point of careful measurement, careful mathematics, and enough patience to run a spacecraft's data backward and forward across millions of years. That is in the end the real subject of this entire story. Not a specific star, not a specific set of comets, not a specific, still debated connection to a climate transition that occurred long before any human being existed to notice it. The real subject is the fact that we now possess the tools, genuinely new tools, built within the lifetime of people still alive today, capable of detecting an event that left no visible trace, that unfolded in complete silence, at a distance and on a timescale that would have made it permanently entirely invisible to every single generation of human beings that came before this one. Consider what that actually means, held up against the ordinary sweep of human history. Every civilization that ever built a monument to the sky, that ever tracked the movement of a comet across the horizon and wondered what it meant, that ever looked upward and asked some version of the question this whole documentary has been quietly circling, was working entirely blind to this particular truth. They watched the same comets you might watch tonight, streaking across a sky they assumed was simply behaving as it always had, with no way of knowing that some of what they were seeing was the visible tail of an ancient, silent collision between our solar system and a star that had wandered too close. That knowledge belongs, in its entirety, to your own moment in history. It did not exist a century ago. It barely existed a decade ago. It exists now, tentatively, carefully, still being tested, still awaiting the December data that may sharpen it into something closer to certainty, or soften it back towards speculation. There is a version of this story that would end on pure unease, and it would not be dishonest to write it that way. A star came close enough to disturb the ancient reservoir surrounding our entire solar system. Comets are still falling as a result, right now, tonight, somewhere out past the orbit of Neptune, on trajectories set in motion before your species existed in its current form. Another star, closer still, is already scheduled to repeat the process in roughly 1 million years, arriving nearer than the last one did, according to measurements that have only ever moved in the direction of greater concern rather than less, as our instruments have improved. That is all true. None of it needs to be softened or explained away to be told honestly. But there is another way to hold this same information, equally true, equally faithful to the actual evidence, and it feels, in the end, closer to where this story genuinely belongs. What you have actually learnt tonight is not a warning, it is a form of context, arriving at almost exactly the moment in human history when we finally became capable of receiving it. The solar system is not the sealed, static room it has always been comfortable to imagine. It has a history, written not just into the rocks beneath your feet, but into the orbits of objects hundreds of thousands of astronomical units away, objects you will never see directly, in a shell you will never visit, disturbed by a star you will never travel to. And for the first time in the entire history of anything resembling a human civilization, we have found a way to read some small part of that history back. Nothing is coming for you. Not tonight, not this year, not across any span of time that should occupy a single one of your remaining thoughts before sleep finds you. The star that mattered has already passed. Its consequences are ancient, unfolding on a timescale so slow that the difference between now and 1,000,000 years from now barely registers as a difference at all on the scale the universe actually operates on. What remains is simply the quiet, strange privilege of knowing, of understanding, even partially, even provisionally, something true about the deep architecture of the place you happen to call home. A star walked through the outskirts of everything you know long before you existed, long before anyone existed to notice. And somewhere out past the edge of everything you can see with your own eyes, the last of its consequences are still, patiently, quietly, falling. That is the shape of it. A star you will never visit, moving through a shell of ice you will never see, still finishing something it started before your species had a name for itself. Nothing about that story asks anything of you tonight. No warning, no countdown, no reason to hold it any tighter than you would hold any other quiet fact about the sky above you. But maybe let it change, just slightly, the way you look up the next time you happen to catch a clear night. Not with unease, with something closer to recognition. Every comet that has ever crossed your field of vision, every faint smear of light people once mistook for an omen, may carry, folded inside its orbit, the fingerprint of an encounter that happened in total silence, 2.5 million years before anyone was there to see it. The sky was never as still as it looked. It was simply patient, keeping records in a language we only recently learned to read. If tonight's journey through cold stars and older comets was the right kind of company for the hour, consider staying a little longer with this channel. Subscribe so the next quiet mystery finds you the moment it's ready. Leave a comment with the thought that stayed with you longest. We read every one. And if there's a corner of the universe that keeps you up wondering, tell us. It may become the next story we tell you to sleep by. Rest now. The stars will keep moving. You don't have to watch them do it.